Hi, I'm Chloe. I'm a research fellow at the University of Melbourne with specialty in coastal geomorphology and numerical modelling. In this video, I want to talk about some research methods in physical geography, and I'm going to focus specifically on modelling aspects.
Put simply, a model is a representation of reality. It could be used to represent an idea, a process, an entire system. And with this broad definition, you can see that a model might come in many different forms. Even taking something simple like an apple, here are a set of images that are all showing different types of models of an apple. They are all representing this item in some way, shape, or form. We use them throughout science to provide us with a simplification of reality that provides a way for us to explore complex things like datasets, theories, or processes. And this improves our understanding of the something that we are studying, which then helps us to answer our research questions. Through representing and exploring something in this way, we can also use the models in a predictive capacity. There are different ways we can build a model, and I'm going to talk about three common types we use in science and physical geography. The first is a conceptual model, which uses concepts or ideas to represent reality. Here's an example of a conceptual model that you might recognise from physical geography, but I'll come back to the details of that later. We also have physical models. Physical models use an actual physical entity to represent reality. Take the example here of the sandbox experiment. Or there are mathematical models that use equations to represent reality, often solved in a computer program. Considering these three types of models, let's look at some examples. We are likely all familiar with sea level rise, the increase in level of the world's ocean due to global warming. As a coastal geomorphologist, I'm interested in how sea level rise is going to affect coastal systems. So as an example, I'm going to demonstrate how I might use the three types of models we discussed previously to look at the effect of sea level rise at the coast. For our conceptual model, I'm using the example of the Brun rule. Here we have a cross-section of the coast with dry land on the right-hand side and ocean on the left-hand side. In its most basic form, the Brun rule is a conceptual model that describes an idea about how the cross-sectional profile might respond with sea level rise. The rule states that as sea levels rise, the dry land will be eroded and move backwards, and the eroded material will be moved offshore to translate this part of the profile upwards. What's important to see here is not what the theory is per se, but to understand that this is a conceptual model, an idea of how the coastal profile might respond to sea level rise. And here's an example of a physical model that's been built by Beal Science. You can follow the QR code at the bottom of the screen to watch their full video. This physical model is an augmented reality sandbox that uses a projector to allow you to look at the topography of the land. As you move the sand around, the contour lines move too. And there are many ways that you can use this sandbox. Here, they are putting tiny houses on the land and moving the sand around to raise the water level and simulate flooding from sea level rise. There are much more sophisticated and scientific ways of doing this in a physical model, but this is a great educational tool nonetheless. Finally, numerical models. Here's some outputs of a model I built to look at the effect of sea level rise on coastal systems as part of my PhD. If you imagine we are looking from a bird's eye view, the black in the sea and the grey is the beach. We have these tiny undulations along the shoreline at the interface between the beach and the sea. When the simulation plays in a moment, the left image will show the evolution of the shoreline only affected by waves. The image on the right will show the same simulation but with sea level rise as well. As the simulation now runs, we can see that spits are created along the shoreline and translate longshore from left to right. This is due to the waves. In the image on the right, we not only see the formation of these spit features, but we also see the shoreline moving backwards due to sea level rise. So these are our three examples of different types of modelling approaches you can use to tackle the same problem or question. Whilst we have shown that each of these are useful approaches, we also need to be aware of the limitations of the models. Each model type and subtype will have its own unique pros and cons, but here are some general limitations to think about. A model cannot represent everything. In our physical sandbox model, for instance, we are only using one type of sand grain when we know that beaches are composed of many different types of material. There are also things we don't know to include. We haven't discovered everything about everything. For these reasons, we have to make assumptions about the models. The models are also only as good as we can make them. They're only as good as the data we put in, the processes we include, and are also limited by our understanding of what should and should not be included. And this brings us onto the point of complexity versus simplicity. You can try and include as many processes as you think are important and create a complex model. But the more things you include, the bigger the margin for error and the less efficient it becomes. The fewer processes you include, the simpler and more efficient the model, but you lose some of the detail of a more complex model. And of course, there are also hurdles when it comes to testing the model for reliability and having trust in its outputs. Famously, George Box said that all models are wrong. And this is true. With all the assumptions and simplifications, all models are inherently wrong. But the important thing is they can still be useful. So we've talked about what models are, why we use them, different types of models, and some of their limitations. So now if we've decided that modelling is the right research method for us, where do we start? The first thing we need to think about is, what are we trying to find out? What are our research questions? Is there anything in particular that we need to represent in the model? Are there any particular processes we need to include? What do we need in order to build the model, like data, for instance? And then you might want to think about some of the specifics, like what scale are you interested in for the model? You can then think about what sort of model is best suited to your research questions. Is it conceptual, physical, numerical? You also then need to think about what modelling approach to use. Is an empirical model that is based on observation and experiments best suited? Or perhaps a process-based model that represents physical processes that describe a system's behaviour? Do you want your model to be stochastic with elements of randomisation, or deterministic, where the same inputs to your model will generate the same outputs every time? And once you've thought about your modelling approach, think about the model you might want to use. Are you going to create a new model? Are you going to use an existing model? Or perhaps you can build on an existing model to fit it to your purpose. Have a think about your model design. What experiments will you run using the model in order to answer your research questions? How will you test the validity of your results? So here's an example from my research. When I started my PhD, I had these two questions. How does the wave angle influence the shape of the shoreline? And how might sea level rise influence coastal change? From these research questions, I can identify some of the key processes I need to include in my model and other details that might be important, such as the scale I intend to model. I decided that a numerical model approach would be best suited, and I set about building upon a model that already existed in order to make it fit my purpose. Even though I took a numerical modelling approach, I actually used many conceptual models to help me convert my ideas about how the model should work into the mathematics I needed to run the numerical model. Once I had my ideas down, I spent many hours coding and actually building the model. Many hours going back to the drawing board as I hit different hurdles along the way, and many hours testing the model. But eventually the coastline evolution model 2D was born, and this is what it looks like diagrammatically. If you want to read more about this particular model, follow the QR code at the top of the page in the right-hand corner. So going back to my first research question, I was able to use CEM 2D to look at how waves influence the shape of the shoreline. And here are some of those results. So this is a bird's eye view of the coast with a very symmetrical wave climate where waves are coming equally from the left and right hand side of the image. We can create these very symmetrical cuspate features. If we have more waves coming from the left hand side, as we can see in the image on the right, we can create spits along the shoreline. So you can see how I was able to build the model and use it to answer some of my research questions using a numerical modelling approach. So that's all I want to cover in this video, but to recap, Modelling is one of just many different types of research methods, and it is a tool we can use to represent reality. Whilst models are simplifications of reality and inherently are all wrong, they are useful nonetheless. In order to choose the best modelling approach, you need to have a think about what you are trying to find out and select an approach accordingly. Thank you for watching, and if you have any questions, please feel free to contact me.